Okay, guys, so in this video, we're going to talk about nuclear chemistry, at least some of the introductions to nuclear chemistry. So the learning objectives of this video is that number one, we're going to compare and contrast mechanisms and characteristics of radioactive decay. All right, so we're going to look at the different types. There's 5 different types we're really going to discuss. We're going to look at alpha, beta, gamma decays, positron emissions, and electron capture, okay? We're going to complete the nuclear equations for each of those radioactive processes I just mentioned. Okay. We're going to identify the types of radioactive process given in a nuclear equation. All right. So if I give you an equation, can you tell me what process exists or what process is going on? Um, we're going to identify what subatomic particles are involved in maintaining stability. All right. And so, spoiler alert, neutrons and protons. And then C, the last one, or E actually, use the nuclide symbol to predict if the nuclide is stable or what type of decay it will undergo. So if it's going to undergo some type of decay, what will it? All right. And there are patterns that we could kind of look at. All right. So let's go ahead and get started. All right. So let's go through some important vocab terms. Okay. All right. So nucleon is basically the subatomic particles of the nucleus. All right, so your protons and your neutrons, these are your nucleon. All right, your nuclide is the whole entire nucleus of a particular isotope. All right, so protons plus neutrons are your nuclide, right? While nucleon is either a proton or a neutron, okay? Now, your nuclide symbols, Z is your atomic number. All right, so here's an example of a nuclide symbol. All right, so Z is your atomic number. You typically put that in the bottom left. A is your mass number. You write down your top left. X represents the element abbreviation. And so, like a good example of this is 42He. All right, the mass number is 4, the atomic number is 2, and the element is helium. All right, so this is just a really good example. Now, radioactivity, all right, so in chemistry and not in Marvel movies, right? Radioactivity is the spontaneous nuclear reaction that transforms an unstable nuclide into a more stable nuclide. All right, so typically that's how that kind of works. All right, so that's radioactivity. Now, a stable isotope is where a nuclide that does not spontaneously decompose into a different nuclide. All right, and so that's kind of like the 2 different parts. It's either the nuclide is radioactive, that means it's going to spontaneously undergo some type of decay so that way it can become more stable, or if not, it's already a stable isotope and that nucleus is going to kind of live as is unless a chemical reaction takes place. So let's go ahead and talk about each of the decay processes or the radioactive decays. All right. And then I'll show you exactly how it looks like in a nuclear equation. All right. And so the first one we're going to talk about is an alpha decay. Now, in an alpha decay, what always gets emitted is an alpha particle. All right. So an alpha particle pretty much is just a helium. All right, it's a helium nucleus. Most times, sometimes you see them written as this. All right, but it's pretty much a helium nucleus. But most cases we do not include the charge to go with it. Okay, or other words, sometimes that we typically write it as a 4-2, and then we have the alpha symbol. All right, and so an alpha particle, it's released or it's being emitted. All right, so let me write or show you an example of how this looks like. All right, so let's just say we have a 238 uranium. Okay, now this uranium is radioactive, and so it's going to go through a decay. Okay, and so it's going to go through an alpha particle decay. All right, where it's going to emit an alpha particle. All right, and so how would that look like? Well, first we're going to write our alpha particle. Okay, and through the law of conservation of matter, like nothing is ever created or destroyed, right? And so the mass numbers and the atomic numbers must be conserved on both sides of the equations, okay? And so what I mean by this, since I have 238 mass number here, the mass number must be 238, or the sum must be 238 on the other side of the equation. Same thing here. Since the atomic number is 92, the atomic number on the right side must equal 92 as well. So since it's 238, here we have emitted four nucleons, all right? And so then we must make sure that both sides must equal 238. So this is going to be 234. All right. And since the left side here is 92, the right side must equal 92. So it is 90. You go look in the periodic table, you find element 90, and you see that it's thorium. All right. And so this is a nuclear equation showing the alpha decay of uranium in this case. So let's go ahead and move on to the next type of decay. So the next type of decay is what we call a beta decay. Now, in a beta decay, you will have a beta particle that is emitted. All right. So, or we call it beta particle emission. All right. Now, a beta particle essentially is really just an electron. All right. That gets emitted. And so sometimes we say beta particle emission or electron emission. All right. And so the symbol, it tends to look like this. We will write 0, -1, all right, emission, or 0, -1 beta. All right. But what ends up happening through nuclear, through this nuclear reaction here, you will see that there is this decrease in the atomic number. All right. And so it's not strictly like an atom that's losing an electron, but in a sense that a and it gets really kind of complicated here, more than I'm going to really kind of talk about in this video. But basically, in a sense, is that it's kind of like losing a proton, but an electron is getting emitted. But as I said, beyond the scope of this video. But the whole idea that is you have this beta particle emission where the nucleus is changing, okay? And so how does this looks like? All right, so let me show you an example of this. All right, so let's say we have carbon 14. Now carbon 14 is going to go through a beta decay. All right, and so how will this look like? Well, here's your beta particle. All right. And so remember, law of conservation of matter. All right. And so these numbers, your mass numbers must remain conserved. Your atomic number must remain conserved on both sides of the equation. All right. And so that means your mass number should still be 14, right? But in your atomic number, since this number is 6, these two together must be 6 as well. So in this case, it will be 7. All right, because 7 minus 1 is equal to 6. All right, and when you look at the periodic table, what element is element number 7? We have nitrogen. All right, and so this is an example of a beta decay. All right, so the next type of emission, we have what we call a positron emission. Now, positron emission, you could kind of think about it like a positive electron-ish, right? And so where it's really small, doesn't really have much of a mass, but it has a +1, all right? Or another way that they kind of look at this is a 0 + 1 beta, because it's kind of like a beta particle, but it's a positively charged. Okay, so this is what we call a positron emission. All right, so this positron is being emitted. So let's look at an example. Let's just say we have a radioactive sodium ion, right, or sodium. And so this radioactive sodium is going to go through positron emission. All right. And so that means this positron particle. All right. We have this positron particle. All right. And so remember, our mass numbers, our atomic numbers must be conserved on both sides. And so the mass number in this case, since the positron mass number is 0, that means this new substance here, its mass number will be 22. All right. And then we got to think about this here. So this is a +1. So what +1 is equal to 11? And for our purposes, it will be 10. All right. So when we look at the periodic table, you look for element number 10. We find that element number 10 is neon. So this is an example of a positron emissions. All right, so the next type of radioactive decay is what we call electron capture. All right. And so now, which is kind of different from beta decay. Decay, we had the emissions of electrons. All right. This one, electron capture, basically we have an absorption of an electron. All right. And so the particle is still an electron or a beta particle. All right. But this time, instead of being emitted, it is being absorbed, it's being captured. All right. And so let me show you exactly how this looks like. And so let's just say we have titanium 44. All right. And it's going to undergo this electron capture. That means it's going to take in this beta particle. All right. So now this, for once, you have this particle that's a reactant. So it's absorbing this beta particle. All right. And so what ends up happening is that the mass number is still 44. All right. 22 minus 1, in this case, is 21. And so what substance, what element is element number 21 on the periodic table? It is scandium. All right. So this is an example of an electron capture. All right, the last one is a gamma ray emission. Now, gamma ray emission is basically very high energy photon, right? So since it's a photon, it doesn't really have any mass per se because it's just light energy. All right, but oftentimes you will find gamma ray emission tends to accompany other type of radioactive decay, right? And so you may have it to where, like, for example, where we have the decay of uranium 238 92, right? It may go through both an alpha and a gamma ray emission, all right? And so we will have our alpha particle here plus our the results from this alpha particle being emitted. And then at the same time, we may have some gamma particles or gamma ray photons that's emitted as well. So gamma ray emission, you typically find this symbol here letting you know that we have this very high energy photon that's being released. But as I said, it doesn't affect the mass at all because the mass of this photon is both zeros, right? The mass of the mass number and the atomic number. All right. But oftentimes you will see this accompany some other type of radioactive decays. We are able to predict what mode of decay a radioactive element or atom will go through. All right. And now there's a couple of things that we kind of look at and a couple of patterns that chemists have found in terms of how a particular element decay naturally. All right. Or what type of decay we find in nature. Okay. And really the two things that we kind of look into is the atomic number versus the mass number and what is the average atomic mass that we typically find on the periodic table. Okay, and so let's kind of explore this. So what you see in front of you is kind of like a roadmap to help you kind of figure out exactly what type of decay most likely will take place. All right, and so typically you will kind of want to start here in this triangle. All right, you want to evaluate the atomic number Z. All right, now if the atomic number is greater than 83, all right, any element that's greater than 83 or 83 and above, really, um, is basically a radioactive element. All right, so all these elements that's bigger than lead, all right, will decay on its own. All right, and so what type of decay that you will typically see? It will be an alpha decay. All right, so like for example, if we were looking at, so let's say we're looking at thorium, right? Where it's like 234, thorium 90. Okay. And so simply for the fact that its atomic number is greater than 90, all right, it's going to go through an alpha decay automatically. All right. And so if you were to write out this equation, this nuclear reaction, all right, we said that it's going to have an alpha decay. So it's going to it's going to emit an alpha particle or helium, really. And then what's going to happen, that it's going to make, then in this case, all right, element 88, which will be, according to the periodic table, radium. Okay. And so, and then you could kind of see, because this is 88, which is greater than 83, then radium in and of itself is going to go through this alpha decay series of decays. Okay. And so that's how, you could kind of look at this. All right. Now, this will continue to kind of take place. All right. So once you go through this alpha decay, all right, what you'll find is that you want to reevaluate your atomic number, and you want to see if the atomic number is greater than 83. All right. Now, if it's not greater than 83, then what you're going to do, you're going to compare the mass number A to the stable mass. Now, what do we mean by stable mass, right? You kind of want to look at the average atomic number that you find on the periodic table, okay? And so because you want the mass numbers to be relatively close, to the average that we find on the periodic table. Okay. So, like, for example, let's just say we're talking about like 12C6, right? So, what you're doing is that you are comparing the mass number A with what we find on the periodic table for carbon. Now, if you go to carbon, you look at its atomic weight, we find that its mass number is 12.01. All right. And so now when you're looking at this, it's like, okay, this number is relatively the same as this. So if the mass here is equal to this, or very, really, very, very close to it, then we have ourselves a stable isotope. Okay. Now, what if it's not, right? So if the mass number of the atom is too high, we're going to go through a beta decay. Okay. And that's it, because there's too many neutrons, so a neutron has to go. All right. Or if the mass number is too low, that's because there's too many protons, then we'll go through some type of positron emission or even electron capture. Okay. And so let's kind of talk about this. Let me show you examples of how that looks like. Okay, so let's look at an example where the isotope mass number is higher than to what we find as the average atomic mass on the periodic table. All right, so let's think about carbon 14, right? So we've heard of carbon 14. Carbon 14 is typically the isotope that's typically used for carbon dating, so to see, how old maybe a particular fossil may be that is found that has been unearthed, right? Carbon 14 is actually a radioactive isotope. And so what they're able to do is measure how much of that carbon 14 is there, because there is typically organisms that are living makes carbon 14 all the time. And so once we die, the amount of carbon 14 there starts to deteriorate over time, or it goes through radioactive decay. Now, what type of radioactive decay does carbon 14 go through? Well, if you look at the periodic table, we see that its average atomic mass is 12.01. So what we find here is that the mass number is actually higher, or in this case, is a little bit too high compared to this average. So that means that this isotope is unstable, and it's going to go through some type of radioactive decay. What type of radioactive decay? Well, when the mass number is high, then we're going to have a beta decay. So carbon 14 is going to release beta particles. So when it releases beta particles, you have a 0, -1, you have this electron here, or you just correct the beta sign. All right, what's going to happen is that now you're going to have, remember, your atomic numbers must be conserved. All right, and so 1 minus what, or what minus 1 is equal to 6. In this case, it'll be 7. All right. Your mass numbers are conserved as well. And so this is element nitrogen. All right. And so when you look at the periodic table for nitrogen, we see that its average atomic mass is 14.01. So you're pretty much right on the money. So this isotope of nitrogen is going to be a stable isotope. All right, so it's no longer radioactive, and then we have this nitrogen that's pretty much sticking around. So that's an example of when we have a mass number that's too high. What about if we have a mass number that is too low? Okay, well, let's look at this example here. Let's say we have this radioactive isotope of titanium. All right, what we find on the periodic table, the average atomic mass of titanium is 47.87. Okay, and so this mass here of 44, it's relatively lower than this 47.87. So this titanium is radioactive. It is unstable. All right, and so what type of radioactive decay is it going to go through? Well, it's going to go through either a positron emission or electron capture. Either or is going to get you about the same answer. Okay, and so let's do a positron emission. All right, so it's going to emit a positron. All right, and so if it emits a positron, it's going to be 0 plus 1. And so remember, beta particles we essentially show is like an electron. All right, and remember that your mass numbers and your atomic numbers must be conserved. All right, so this is 21 over 44. What element is element 21? It turns out to be scandium. When you look at the periodic table, we see that the mass number of scandium is 44.96. And that's pretty close to this 44 here. So right here, the scandium is going to be a stable isotope. Okay. Now, what if we go through electron capture, right? So same thing here. So we have this titanium is going to go through an electron capture. So it's going to take in this electron. All right, what do we have here? Well, this is 2144 scandium. All right, and so you notice it's the same answer here. So regardless of whether it goes to a positron emission or electron capture, you'll come out with the same result. All right, the same new atom is going to be formed. In this case, we got ourselves a neutral atom. All right, so as I said, all depending on what's going on. If you kind of use this chart here to show you where you're going, start here. All right, is if your atomic number is greater than 83, alpha decay. That's what's going to happen. And it's going to keep on alpha decaying until the atomic number is less than 83. Once it's less than 83, you want to compare your mass number to the average atomic mass that we find on the periodic table. All right. If the isotope number is too high, we're going to go through beta decay. All right. And that's going to happen until you go back here and then your mass numbers are equal. If your mass numbers are too low compared to the average, then we'll go through either some type of positron emission or some type of electron capture. All right. And so that concludes this video.